Section 3.5, we're going to use our knowledge of truth tables to analyze arguments and to decide whether an argument is valid or invalid. Notice the difference between a statement being true in our real world and a result of an argument being valid. You can have a valid argument that ends up with an untrue statement, so be careful. The idea in problem 38 is that we are going to assume that two things are true. We are going to assume that it is true that we will go for a bike ride or we will go shopping. We're assuming that that's true. Doesn't matter if it's really true or not, we're assuming for the purposes of this argument that it's true. We're also assuming that we will not go shopping. So for the purposes of this argument, we're making those two assumptions. Regardless of whether they're really true or not, we assume them to be true. Now, based on those two assumptions, what we want to know is, does this have to follow? Based on these two assumptions, does this result logically have to follow? Is it airtight? Well, we can do that. The first step in doing this is to create some variables and make a symbolic argument. So it looks like we need a statement P that says we go for a bike ride. And we need a statement Q that says we will go shopping. And we need to make some sort of symbolic argument. So let's translate the original problem into symbols. We will go for a bike ride, that's P, or we will go shopping, that's Q. And then we will not go shopping, that's the negation of Q. And therefore, we will go for a bike ride, that's P. So this is the same argument as this one, but it's written now in letters, and that has some real advantages, one of which is we can make a truth table for this. Now, the way to make a truth table for an argument, if you're trying to decide whether it's valid or not, is to take all the assumptions, we have two of them, and connect them with ands. So we will put one of the assumptions, P or Q is true, and we'll put the next assumption, the negation of Q is true, and then you put implies, an if-then, and then you put the conclusion that you're trying to prove. And what you want to do is analyze this statement with a truth table. So let's just go ahead and do that. We have P and Q. We kind of know how this works. We've done it often enough. And so then we have P or Q. Ors are true unless both are false. And we have the negation of Q. And then we have P or Q and the negation of Q. So that's an and connecting these two things, and ands are usually false unless both are true. And then we have this statement. Instead of writing it like I should write this statement right over here. I'm just going to put an arrow that says that statement goes there. And the only way that it could be false, a broken promise, is if this part is true and this P over here, the second part, is false. So do we see a true here and a false here? Well, there's only one true here, and it's true over here. So there is no place where these are true and these are false. Therefore, this statement on our truth table is always true. It's a tautology. And when that happens, that shows that the original argument is valid. Whoa, valid with a W. That makes very little sense. And what does that mean? That doesn't mean that this is true in the real world. It doesn't mean that you have to go for a bike ride. That's not really what's going on. What it means is if we assume that these premises are true, then based on those being true, this must be true. There's no way it can be false. And there's one other thing I'd like you to notice. I think this is the best way to do the problem. I think this is the way you should do the problem, more or less, period. We've been studying truth tables, and you should do the problem this way. However, if you look on page 140, some of the most common arguments are outlined, and if you get to one of those, you could just quote it if you had them memorized and you understood them. So look at page 140, see if you can find something that looks like this. I'm not sure if you can or not, but if you could find something that looks like this, then you could quote that. And if you can't find something that looks like this, then you can't quote it. So once again, we have an argument. I've taken the argument and used their words and written in this format where we can see the first assumption or premise, the second assumption or premise, and then based on those being assumed to be true, whether they are or not, doesn't matter. Then the question is, does this have to follow? Must it follow? Or is there a way that these two could be true and this one could be false? And so the question is, if we make an argument like in the last problem, do we get our truth table to give us all truths? In order to do that, I defined two variables, p and q, and then rewrote this argument using the q's and the p's. And now we can use this to build our truth table. So we take the first premise, which is this, and we do an and with the second premise, which is this, and then we do if-then, or an implication or a conditional with this conclusion. And so we know how to set this up. We've set this up so many times it would be hard to do it wrong. But once in a while we could do it wrong anyway, just for fun, I guess. It looks like I'm going to need a not p, so I might as well stick that in somewhere. And then we're going to need this, q or not p, q or not p. And that's these two. Ors are almost always true unless both statements are false. And then we need this and p. And so we're going to do q. And perhaps I should have been drawing some separators here. I don't know. Sometimes I do when things get kind of big. So we're going to be doing these two with an and those are true and both parts are true. And I don't see that it's true very often. It's true there, but there's no other place where it's true. And now we have to do this. And on these last ones, I'm kind of in the habit of just doing this instead of writing it all down. But it's up to you. Maybe that doesn't appeal to you. Maybe you want to write it all down. I don't know. So now we're doing a conditional starting with this and ending with q. And so we're interested in when this is true and this is false, because that's the broken promise. That's false. But there's only one true here, and it's true there. So there's never a broken promise. So this statement is always true. So it's a tautology, and that means that our original argument is valid. And once again, that doesn't mean that it's true that the printer has a clogged nozzle. That means if we assume this is true, and we assume this is true regardless of whether or not they're actually true, if we make those assumptions, then this has to be true. That's what it means to be a valid argument. If there had been one of these being false, then this would have been an invalid argument.